Hi there, my name is Philip Venturelli and I am a Caltech alumni. I graduated in 2002 with BS in physics. I've been working on a project of my own for the past year or so involving space exploration and developing technologies for space exploration. Wanted to share this presentation with you. It is called Firecat, and it is basically a robotic imaging system designed to further the exploration of asteroids, comets, meteors, and earthbound space debris. So, without further adu, I will begin. A large collection of retired satellites orbiting the Earth forms our earthbound space debris. And I believe there's something in common between our man-made debris around Earth and the naturally occurring asteroids, for example, the main asteroid belt by Mars. And that is that if you approach it from the point of view of resource utilization in space for development and exploration, you could recycle stuff from the old satellites, enabling you to build things in near-Earth space or cislunar space closer to the orbit of the moon. And also, likewise, in the Mars area, if you don't want to have to lug minerals that you need for constructing things from Earth, then there may be ways to robotically harvest some of the materials present in the asteroids and make use of them in the Mars area or gravitational sphere of influence. So that's the basic idea behind this technology that I've been working on, and I'd like to I've only got a few slides here, so this won't take long. I'm just going to go over a few more points on how you could, what would be the first step, really, to doing this, because the robotic systems are not currently available from a technological standpoint. We haven't had any experience building robotic systems that can mine and harvest and recycle materials from space. So before we go down that road, I believe it would be useful to try and develop an imaging system that could map the materials and their locations that are present in any of these debris constellations. If you could map them, then you would be able to design a mission that would most efficiently go out there and collect the things you need. So that's the basic idea. So the word that people use to describe this process is called characterization, in contrast to things like detection and tracking. Characterization is a more detailed type of imaging objective. I've worked in the aerospace industry for about 10 or 15 years on infrared optics and infrared spaceborne sensors and imaging systems. And characterization is a more sophisticated design objective or mission objective than the basic, detection or tracking, which is basically looking for, reflected sunlight glint off of an object and making sure that it's present in the orbital path or resolving the orbit of a space object, which would be tracking or detection. Characterization is looking at that space object and saying, okay, what's it made of? So that's what we need to do here. So you're using remote observations, and the main tool I think we would have to use for this would be some form of spectroscopy, where you can actually analyze the frequency spectrum of the light that you're seeing, and so there's other approaches. You could use either a passive or a active type sensor. Passive sensor is probably preferable, and that would be just looking at reflected sunlight and seeing if you can analyze that and basically do some noise filtering and then determine what the actual material composition could be of that object. And I'm going to talk about this in a minute, but if you're dealing with something that has man-made internals, you may want to merge that with existing knowledge on which satellites are up there, and use an algorithm to try and correlate the things you do know already about what's up in space versus the spectrum that you're receiving, and see if you can match that information. But that being said, for spectroscopy purposes, a very useful technology is called a multispectral sensor. So let's go into that right now. A multispectral sensor is basically like an ordinary, similar to an imaging sensor like a CCD chip, except for the fact that it has several different planes. Each plane has a different frequency response. So you can actually look at, for example, this is a spectrum of a hydrogen atom. You wouldn't necessarily be looking for hydrogen, but it's simple here. So the point would be the atom or the substance absorbs energy in one frequency band and radiates energy in a series of other frequency bands. If you can, if say there's 4 frequency bands, a red, green, blue, and a purple, if you can actually have your CCD chip be sensitive to all these 4 different frequency bands, so that the data that comes back from each band is basically separate from the others, then you have 4 unique ways of looking at this object from 4 different frequency bands. So that, in a nutshell, is a multispectral sensor, and those things do exist. And I think that would be a useful tool for this mission. So to increase the chances of identifying a spectra, there's the sort of the first thing that you might think of, which would be basically oversampling the spectrum. This is not physically possible. What that would mean is, if you were to have like 1,000 different frequency bands, you don't know. You say you have a list of possible things you're looking for, different elements that you'd be looking to harvest. Well, each one has a different frequency response, or they reflect light in different ways. You have different radiating bands, essentially. So if you think of all the possibilities that you might be looking for, you could try to hope that you could build something that could have 100 or 1,000 different frequency bands, 100 or 1,000 different planes to your CCD array, which is your multispectral sensor. That's not possible. It's just too difficult to build that. Typically, you get maybe 3 or 4 or maybe 5. So the question then becomes, where would you like those frequency bands to be so that you could be most likely to find the elements or compounds, minerals that you are actually actively looking for? So this is a different approach than the brute force oversampling approach, which is not practical. So I suggest, I would propose to use some form of algorithm, perhaps an artificial intelligence algorithm, that could match some of the data, simulated spectra, with so essentially you're solving the problem in 2 different directions. Number one, forwards, which is you're synthesizing essentially what the spectra would be based on a simulation. So you're coming up with, you have a computer simulation, and probably you wouldn't have to start from scratch on this. I I think there are things out there that are available for free, but you could simulate carbon or copper or aluminum, and you could introduce the noise patterns from perhaps surface features on the object, the lighting from the sun, sort of the broad spectrum lighting from the sun, and other variables that might produce noise, including the detection noise, which is noise introduced from the sensor itself, dark current or thermal noise in the sensor, glare from the optics. You could introduce a bunch of these different layers of noise, and you could simulate a spectra that you'd be seeing, and then you could try to tweak your frequency planes so that you can optimize essentially your best chances for detecting the things that you care most about, based on the several runs from your simulation, probably some statistical approach like Monte Carlo simulations or something like that would allow you to come up with some idea of where those frequency planes should be to maximize your chances of seeing what you're looking for. So that's one approach. To go more detailed into it, you could think about using what's called a genetic algorithm. Now, this is something that JPL has been successful with in actually helping to develop, I believe, the wheels or the shock absorbers on some of the Mars landers, where the mechanical construction was optimized using a genetic algorithm. So you could basically think about taking some of the design variables and the location of the frequency planes or something like that, and you can probably want to correlate that with what's actually feasible in terms of fabrication procedures, but that's just a sanity check. But from the algorithm standpoint, you'd want to take a few variables, identify what those are, so that you could wrap a genetic algorithm around that, which basically simulates the environment. It's sort of if you think of the way biological systems work in nature, they evolve in response to environmental variables. So there's this part of the genetic algorithm is taking what are called the phenotypes, which would be your design variables, and doing some sort of combination process where they're being mutated and replicated and things like that within the algorithm, and their evolution is governed by the response to the environment, which in this case would be the spectra and all of the factors giving rise to the spectra. And then some of those pathways are continued, and other ones are halted, and you come up with what's basically an optimal solution for your engineering variables, like where would those frequency planes be. So that's a more sophisticated approach to doing this. Now that leads to the question, what would those design variables be? I mean, there could be other ones besides the frequency planes. There could be numerous variables. Typically, if you got about 10 of them, that's probably good. So I'll just open that up to you guys. What do you think those design variables could or should be? We're thinking about spectroscopy in a broader sense, perhaps multispectral sensing. What kinds of systems and technologies and what kinds of parameters at the engineering or design level would we need to trap and evolve using this type of algorithm? So that's an open question. Okay, so in terms of strategic development or strategy, some rough calculations I did, probably not a surprise. There's several orders of magnitude more sunlight bouncing off that space debris. If you put an observatory on the surface of the moon, looking at the earthbound debris in maybe geosynchronous orbit, you got a decent amount of light coming back. I think it's like 10 to the 6 photons per second. Whereas if you look at sunlight bouncing off the main asteroid belt and hitting a telescope on Mars, you're probably at 600 photons per second. So that determines the signal level, and it's always a balance between signal and noise in these types of things. So the noise sources are probably the same. The signal sources are many orders of magnitude less for Mars. So it might make sense to try and to do your initial development in the Earth-Moon system with the Earthbound space debris. And then once it's been optimized and refined, you can probably think about putting it in other places like Venus. And by the way, some of the recent news has involved finding about 100 or so asteroids in orbit around or very close to the orbit of Venus. So in the inner solar system, where light is not a problem. But just for simplicity's sake, here we are, on Earth, and so might as well do something easy and accessible and develop it closer to home, and then move it elsewhere if that is the future design pathway. So that's my strategy comment. So basically, in a nutshell, summarize everything. Extensive simulations. We'll use computers and simulations to do some of the more tricky design aspects. Determine what type of multispectral or spectroscopy variables and design would be best for the different missions. So you got the Earth case, the Mars, and the Venus. Probably some variables would be unique to each case. So map it out, just to get a look at where the technology is headed, and then try to make a bridge towards the practical side, the fabrication. What can be built, and how can we make recommendations to a sensor shop and tell them a few things about the sensor we're looking for, and they could build it for us, build it to the design specifications. Could we? Another question is, do you think we could close on our objectives? Would we be able to reach a reasonable, what's a reasonable statistical level of certainty here? Probably, I would say anywhere upwards from maybe 70%. If you want to be sure, put it up in the 85% likelihood of detection. Probably there's a distribution associated with the various different materials we're looking for. And you're really just trying to perhaps either hit a sweet spot or make the distribution as broad as possible, so that you hit as many of the desired minerals. Another question is, I don't have a whole lot of insight as to what those desired materials would be for space development and engineering. I know people thinking about going to the moon and processing materials on the moon or on Mars had put some thought into that. So what kinds of elements do we need? What kinds of elements and molecules do we need that would allow us to do the fabrication that we're hoping to do in space? A microfabrication, perhaps, using maybe you could think of using some sort of a laser metal deposition printing system to. I know those technologies are available on Earth, and we can print out turbine blades for F-14s from an aircraft carrier in the ocean. So a similar situation, making parts and components for space vehicles or satellites, those kinds of things. What type of materials are desired? Probably a lot of metallic compounds. So probably would be useful to have a list of those as well. So that's all I have on this. I think this would be a good location for the first Firecat observatory system, looking back at the Earth and seeing the whole cosmos, but in perspective of the cosmos, we would see the Earth-bound debris belts and be able to map them and characterize them, which, by the way, according to NASA, is considered a a useful and desirable technology. So that's all I have, and I'd love to hear your comments and thoughts. Thanks for your time. Bye.